Every problem that evolution encounters gets a solution. That's the entire mechanism. When predators evolve sharper teeth, prey evolve thicker hides. When predators evolve better tracking abilities, prey evolve faster speeds. It's an endless refinement, an arms race that stretches across millions of years, with neither side ever gaining a permanent advantage. And most of the time, balance is maintained. The predator and prey populations regulate each other. Neither gains overwhelming dominance. It's brutal, but it's stable. But occasionally, evolution doesn't find balance. It overshoots. It produces a solution so extreme, so disproportionately powerful, so architecturally over-engineered, that it ceases to be a defense mechanism and becomes something else entirely. A liability. A burden. A weapon so effective that the prey species wielding it ended up killing more of their own kind than any predator ever managed. This is the story of when evolution won the arms race so decisively that it accidentally created species that didn't need protection from predators because they were too busy being threats to themselves. We start with something that shouldn't exist, a 5-meter-long, 5-ton herbivore with 1-meter-long claws. The Therizinosaurus was an absolute anomaly, a theropod dinosaur built on the same body plan as Tyrannosaurus rex and Velociraptor, but instead of teeth engineered for killing, it had flat molars designed for grinding plant material. Instead of arms optimized for grasping prey, it had 2.5-meter-long forelimbs, equipped with 3 claws, each one between 70 centimeters and 1 meter long, each one curved and blade-like, capable of slicing through hide and muscle in a single motion. To put that in perspective, the longest claw ever measured on a Therizinosaurus was 91 centimeters, or about 3 feet, longer than a baseball bat. Attached to an arm longer than most humans are tall, from an evolutionary perspective, this makes no sense. Why would a plant eater weighing as much as an elephant need weapons powerful enough to tear through the hide of a sauropod? Why would evolution spend energy developing tools designed for combat when the animal's entire feeding strategy centered on vegetation? The hypothesis some paleontologists arrived at is unsettling. Those claws may not have been primarily for fighting predators. They may have been for fighting other Therizinosaurus. Therizinosaurus fossils are rare and fragmentary. We don't have the sample size to make definitive claims. But the specimens we do have show deep gashes that match the dimensions of those 1-meter claws. Wounds consistent with violent encounters between individuals of the same species. Not predation attempts. Intraspecific conflicts. And when you're wielding claws engineered to slice through thick hide and muscle, and your opponent is wielding identical claws, what should be a territorial dispute becomes something far worse. Imagine being a Therizinosaurus. You're a solitary animal. You encounter another member of your species maybe a few times a year, and every encounter carries the risk that one scratch becomes a wound, one wound becomes a severing, one severing becomes death. So this 5-ton herbivore carrying claws that could disembowel any predator in its ecosystem may not have needed those weapons to survive predation at all. It needed them because evolution had made intraspecific competition the bigger threat. The predators never stood a chance. But neither, it seems, did the Therizinosaurus. If Therizinosaurus evidence is fragmentary, the Stegosaurus left us something definitive. The Stegosaurus was 9 meters long, weighed up to 5.3 tons, and carried 4 large spikes on its tail, the thagomizer. Each spike measured between 60 and 90 centimeters long, made of solid bone, wickedly sharp, attached to a tail that could swing with enough force to drive them through dinosaur bone. From a defensive perspective, these spikes were brilliant. They made the Stegosaurus's rear quarter a weapon. A predator attacking from behind, which is the safest approach for most predators, would encounter something specifically designed to pierce and kill. And we know it worked. In 1999, paleontologists found an Allosaurus pelvis with a hole punched clean through it. A wound roughly the size of a human fist. The puncture matched Stegosaurus spike dimensions exactly. The Allosaurus survived long enough for the bone to start healing, and then developed a massive infection that killed it weeks or months later. One specimen, one documented kill. But that single fossil tells us something important. The thagomizer wasn't theoretical. It was lethal. Here's what makes this darker. The Stegosaurus probably wasn't trying to evolve a weapon that killed predators efficiently. It was evolving a weapon that killed predators at all. The thagomizer was a desperation mechanism, a leave-me-alone tool. But desperation tools don't come with off switches. If you can pivot and drive a 90-centimeter spike through an Allosaurus pelvis, you can pivot and drive that same spike through another Stegosaurus. During territorial disputes, during mating competition, during any encounter where 2 5-ton animals with lethal rear quarters got too close to each other, We don't have fossil evidence quantifying how many Stegosaurus died from thagomizer wounds inflicted by their own kind. But we have a weapon designed for maximum penetration, attached to an animal that lived alongside others of its species. The math isn't comforting, but if you think the Stegosaurus had problems, the Ceratopsians turned horn combat into an art form. Triceratops, Styracosaurus, Centrosaurus. The Ceratopsians were herbivorous dinosaurs whose defining feature was massive facial horns. Triceratops carried 2 brow horns up to 1 meter long, 1 nasal horn around 30 centimeters, mounted on a skull that measured 2.5 meters from beak to frill edge. The entire animal stretched 9 meters long and weighed between 6 and 12 tons. Paleontologists spent decades assuming these horns evolved as defense against predators. A 12-ton Triceratops charging at a Tyrannosaurus rex with meter-long horns forward would be genuinely terrifying. But the fossil evidence told a different story. Ceratopsian skulls frequently show horn-shaped puncture wounds on the sides and frills. A 2009 study examined over 400 Triceratops specimens and found that 14% of squamosals, the bones forming the frill's side edges, showed healed puncture wounds. The holes matched horn dimensions exactly. Not deep enough to be fatal in most cases, but deep enough to indicate repeated encounters. Multiple wounds on multiple specimens, some healed, some fresh. Some individuals bore evidence of surviving multiple horn strikes over a lifetime. The horns weren't primarily for predators. They were for establishing dominance within the herd. Ceratopsians lived in herds, confirmed by fossil trackways, bone beds, and growth patterns. Within those herds, dominance had to be established, resources contested, breeding rights determined, and the mechanism for resolving these disputes was the horns. Triceratops fought Triceratops, Styracosaurus fought Styracosaurus. Regularly, bloodily, with weapons capable of piercing bone. So here's the irony. The horns may have been so effective at making Ceratopsians dangerous that predators often left them alone. Without constant predation pressure, the horns became instruments of internal competition, hierarchy establishment, intraspecific violence. The weapon that was supposed to protect them from predators may have ended up being used primarily on each other. Now we get into something genuinely contentious among paleontologists: the dome-skulled dinosaurs. Pachycephalosaurus had a skull with a dome of solid bone 25 centimeters thick, roughly 10 inches of solid mass sitting on top of its head. The animal itself was about 4.5 meters long and weighed around 450 kilograms. But that skull was reinforced with struts and support structures that made it disproportionately massive. The spine was built to absorb impact. The neck muscles were configured for collision force. For decades, the assumption was obvious. These were battering rams. Males locked skulls in dominance contest. The one with the thickest dome, the strongest neck, the most effective charging technique got to breed. But here's where science gets complicated. Some biomechanical studies suggest Pachycephalosaur skulls weren't actually suited for direct frontal collisions. The dome shape might have caused glancing blows rather than direct impacts. The bone structure shows characteristics that some researchers interpret as better suited for flank butting, striking opponents from the side rather than head-on ramming. Other studies disagree. They point to specimens with impact fractures, dents that match the size and shape of other Pachycephalosaur domes. Damage patterns, suggesting not one fight but accumulated trauma over a lifetime. The debate isn't settled, but here's what both sides agree on. Pachycephalosaurs evolved 25 centimeters of solid skull bone that required enormous metabolic investment. Whether they used them for direct combat, flank attacks, or aggressive display, they evolved a structure so extreme that it dominated their anatomy. And there's no predator in the Mesozoic that would have benefited from a Pachycephalosaur charging at it head first. Whatever those domes were for, they weren't for external threats. They were for each other. Everything we've covered so far involved specialized weapons. Now we look at what happens when the entire body becomes a weapon. Complete impenetrable armor. Ankylosaurus was a walking tank, 6 to 8 meters long, 4.8 to 8 tons. Covered in osteoderms, bony plates embedded in the skin, some measuring 35 centimeters across. Studded with spikes along the flanks. Equipped with a tail club made of fused vertebrae, measuring up to 60 centimeters wide and capable of generating impact forces that some studies estimated over 4,800 newtons, enough to shatter bone. The entire body was engineered to be impenetrable. No gaps, no vulnerabilities, just overlapping armor and defensive protrusions in every direction. From an evolutionary perspective, this worked perfectly. Tyrannosaurus rex would have struggled to find a weak point on an adult Ankylosaurus. Some paleontologists believe healthy adults were essentially immune to predation, but complete armor creates a complete problem. You're now a slow, ponderous animal in a world where mobility matters. An Ankylosaurus maxed out at maybe 10 kilometers per hour. Couldn't outrun anything. Couldn't efficiently migrate. Couldn't escape resource-depleted areas. Every advantage in defense came with a cost and flexibility. And here's what happens when two slow, heavily armored, club-tailed animals encounter each other over territory or resources. They fight. Not with the ritualized grace of Ceratopsian horn duels. These were full-body conflicts. 6-ton animals slamming armored flanks into armored flanks. Tail clubs swinging at bone-plated bodies. Two creatures essentially weaponized into walking siege equipment, neither capable of quickly disengaging. Fossil evidence shows Ankylosaurus bones frequently bearing impact trauma. Fractures consistent with being struck by heavy objects. Dents in the armor consistent with club strikes. So the Ankylosaurus evolved the most effective anti-predator defense in the Mesozoic, and then had to use that same equipment against its own kind during every territorial dispute, every resource competition, every breeding season encounter. The armor that was supposed to be ultimate defense became a burden that made every interaction potentially lethal. We've been talking about weapons. Now let's talk about what happens when the weapon has a 15-meter reach and can't distinguish between enemies and family. Some sauropods, Diplodocus, Apatosaurus, Brachiosaurus, developed tails of extreme length. Diplodocus tails contained up to 80 vertebrae and stretched 13 to 14 meters. The final portion tapered to a thin, whip-like structure that some biomechanical studies suggest could break the sound barrier when snapped, generating tip velocities exceeding 1,200 kilometers per hour. From a defensive perspective, this was devastating. A 14-meter tail moving at supersonic speeds would strike with tremendous force, enough to break bones, enough to cause fatal internal injuries, enough to deter any predator that witnessed it happening to something else. And we have some evidence this happened. Theropod specimens bearing fractures consistent with blunt force impact trauma. Injuries that could have come from a sauropod tail strike. But here's what made this weapon particularly problematic. It was indiscriminate. Picture a sauropod herd. Adults weighing 12 to 15 tons moving together. Juveniles weighing a few hundred kilograms weaving between them. A predator approaches. An adult whips its tail in defense, 14 meters of bone and muscle moving at hundreds of kilometers per hour, and catches a juvenile in the head. We don't have fossil evidence quantifying this. We can't say how often it happened. But the physics are uncomfortable. A weapon that operates in a 14-meter radius, deployed in a social environment where herd members routinely move within that radius, creates risk that isn't limited to predators. The sauropod evolved one of the most effective defensive weapons in the Mesozoic. It just happened to be a weapon that couldn't distinguish between threats and family. We've spent this video on dinosaurs. Now we watch mammals make the same mistakes. More recently, more documentably. Megatherium, a giant ground sloth that stood 6 meters tall on its hind legs and weighed 4 tons. For context, that's taller than a T-Rex and heavier than most elephants. Modern sloths are gentle creatures. They eat leaves. They move slowly. The entire evolutionary history of sloths is defined by not being a threat. Except Megatherium. Megatherium evolved massive forelimbs with claws measuring up to 30 centimeters long, designed to strip bark and pull down branches. But those same claws were devastating weapons. Curved, sharp, capable of causing catastrophic injury to anything in the Pleistocene, including the giant predators of Ice Age South America. And fossil evidence shows Megatherium skeletons bearing claw mark wounds, deep gouges measuring 20 to 30 centimeters long, puncture patterns that match the dimensions of other Megatherium claws. Here was a 4-ton, 6-meter herbivore that somehow evolved weapons powerful enough to deter any predator, but whose primary source of serious injury appears to have been other Megatherium. Males fighting males for territory. Competition during breeding season. The same claws that stripped bark also stripped flesh. But Megatherium was slow, ungainly. Maximum speed estimates put it at around 4 kilometers per hour. An injured Megatherium couldn't efficiently forage, couldn't escape further conflict, couldn't recover easily. The sloth evolved 30-centimeter claws it never needed for survival, and then turned them on its own kind. Everything we've discussed so far is fossil evidence. This next one you can watch on YouTube. A bull moose can weigh 700 kilograms and carry antlers that span 2 meters tip to tip, weighing up to 35 kilograms. That's 35 kilograms of bone growing from its skull every single year, shed and regrown annually. These antlers have tines, points, that can number over 20, each one capable of puncturing hide and muscle. And yes, occasionally wolves kill moose, that happens. Wolf packs take down maybe 10 to 15% of the moose they target. But population data points to something consistent. More moose die from antler wounds inflicted by other moose than from predation. During rutting season, September through October, bull moose engage in antler combat, locking and twisting, pushing, fighting for dominance. These combats frequently result in serious injury. Penetration wounds where tines pierce flesh, broken ribs, punctured organs, internal bleeding. Some moose die from these injuries directly. Others survive wounded, which makes them vulnerable to predation, starvation, or infection over the following winter. Some carry permanent damage, healed fractures, chronic pain, limited mobility for the rest of their lives. Imagine being a bull moose. You survived predators, you survived winters, you grew to 700 kilograms with a 2-meter rack of antlers. And now, the greatest threat to your survival is another 700-kilogram bull moose with an equally massive rack, and neither of you can back down because backing down means not breeding. The arms race between moose and predators stabilized long ago. The arms race between moose and moose never stops. This one is happening right now in African waters, and the numbers are staggering. Hippopotamuses are herbivores. They eat about 35 kilograms of grass per night. They spend their days in water, and they possess a mouth that opens 150 degrees, nearly a straight line, revealing canine teeth that can grow to 50 centimeters long and incisors reaching 40 centimeters, plus a bite force measured at over 8,100 newtons. For comparison, a lion's bite force is around 4,500 newtons. These teeth evolved for vegetation processing, for stripping grass, for grinding plants, but they also kill constantly. In Africa, hippopotamuses kill an estimated 500 humans per year, more than lions, leopards, and crocodiles combined. A 1.8-ton animal with 50-centimeter teeth, a 150-degree gape, and extreme territorial aggression is essentially a biological weapon that happens to eat grass. But here's what makes it relevant to this discussion. More hippopotamuses die from hippo bites than from any predator. During territorial disputes in the water, during breeding competitions, during the constant jockeying for position in rivers and lakes, hippos bite each other with the same lethal intensity they show toward human intruders. Males compete for stretches of river. Dominant bulls defend territories against challengers. And those 50-centimeter canines capable of biting through a small boat are just as effective against other hippos. A hippo that survives a territorial dispute may carry lifelong infections from the wound, may lose functionality from scar tissue, may be weakened enough that the next dispute becomes fatal. Right now, in this moment, in African rivers, hippopotamuses are killing other hippopotamuses with weapons that evolved to eat grass. African buffalo carry horns that curve upward and outward before hooking back inward, creating a span of up to 1.5 meters. The boss, the fused horn base across the forehead, can be 10 centimeters thick, essentially a helmet of solid bone. The horns themselves taper to sharp points capable of piercing hide, muscle, and organ. Adult males weigh between 700 and 900 kilograms. That's 900 kilograms of animal with 1.5 meters of weaponized bone on its head. These horns can kill lions, have killed lions, are documented killing lions with enough regularity that lion prides specifically avoid healthy adult buffalo when easier prey is available. And they kill buffalo too. Buffalo live in herds of 50 to 500 individuals with fluid social structures where status is contested regularly. Territorial disputes happen. Dominance contests happen. Males establish breeding rights through horn combat, clashing boss to boss, hooking and twisting, trying to gore the opponent's flank. And African buffalo horns, while being highly effective against predators, are equally devastating against other buffalo. Penetrating tips, curved designs that catch soft tissue and tear, 900 kilograms of force behind each strike. Modern populations suffer injury rates from other buffalo that wildlife studies suggest are comparable to predation rates. The horns evolved to fight predators. They became tools for interspecific dominance. And that created an environment where being a buffalo means constant risk of grievous injury from other buffalo. Finally, something that shows evolution can overshoot in the opposite direction. The narwhal's tusk. A narwhal is a medium-sized Arctic whale, 4 to 5.5 meters long, weighing 800 to 1,600 kilograms. It eats fish, squid, and shrimp. Relatively harmless in almost every way except for one feature, a spiraling tusk made of tooth material that can grow up to 3 meters long and weigh 10 kilograms. This tusk is actually a canine tooth that grows through the upper lip, spiraling counterclockwise as it extends. It contains up to 10 million nerve endings, making it a sensory organ capable of detecting changes in water salinity, pressure, and temperature. But it also evolved as a dominance display, a visual indicator of fitness. Larger tusks indicate better nutrition, better genetics, better survival capacity. Males with longer tusks tend to have higher social status. And here's where it gets complicated. Narwhals with broken tusks suffer higher rates of challenge from other males. The broken tusk doesn't function as a dominance display. Other males approach more frequently. Conflicts escalate more often. Additionally, the tusk sometimes interferes with basic survival. Getting caught in ice, colliding with obstacles in tight spaces, creating drag during swimming. The tusk is so long relative to body size, 3 meters on a 5-meter animal, that it occasionally becomes more liability than asset. Males with the most prominent tusks don't necessarily have higher survival rates. Studies suggest they have higher injury rates from combat, higher metabolic costs from maintaining such an extreme structure. The weapon that's supposed to signal fitness may actually reduce fitness in some individuals. The narwhal evolved a sensory organ so extreme that it became a weapon, and then that weapon became a burden. An arms race against other narwhals that nobody wins. So here's what we've learned about evolution and weaponization. Sometimes prey evolve defensive mechanisms so effective that they solve the predation problem entirely. The predators stop showing up. The arms race ends. And then the prey turns the weapon on itself, because evolution doesn't care about proportionality. It doesn't know when to stop. It just keeps selecting for more extreme versions of whatever works. Longer claws, sharper horns, thicker skulls, bigger antlers, more lethal weapons, until the prey species becomes the primary threat in its own ecosystem. The Therizinosaurus didn't need its 1-meter claws to fight predators. The Stegosaurus didn't use its 90-centimeter spikes primarily against Allosaurus. The Ceratopsians that evolved meter-long horns to deter predators spent most of their combat time driving those horns into each other. The moose, the hippos, the buffalo, the narwhals. Evolution didn't make them apex predators. It made them apex threats to themselves. Thanks for watching, and until next time.